Hello there, and welcome to Drift to the Stars. I'm so glad you found your way here tonight. Before we begin, I'd love to know, what country are you listening from? And what time is it there right now? Are you settling in alone, letting this carry you towards sleep, drifting through dreams of distant worlds? Or are you gathered around a table with people you love, with the warm sounds of a shared meal nearby? Wherever you are, I'm glad you're here. Tonight we're going to wander somewhere close, and yet almost impossibly strange, a world that has watched over humanity since before we had words for what we were seeing. A world bright enough to cast shadows and old enough to have forgotten more than we will ever know. If tonight's journey brings you something peaceful, something worth holding on to, please consider sharing this video with someone who might need a quiet place to rest. It means more than you know. Now if you're ready, let's begin. There is a world not so far from here where time moves in a way that makes the mind go soft and still. Imagine a single day stretching so long that it swallows an entire year inside it. Not a long day the way a summer afternoon can feel endless, but genuinely and cosmically slow. The planet turns so reluctantly on its axis that by the time it completes one full rotation, it has already traveled all the way around the sun and come back again. A year passes in the time it takes to finish a single day. Venus rotates once every 243 Earth days, while its year lasts only about 225 Earth days. The day is longer than the year. That's not a metaphor. That is simply what is true. There is something in that slowness that feels almost like a kind of patience, as though the planet decided very early on that it had nowhere to rush to, that the light would come when it came, and the dark would come when it came, and there was no need to hurry either along. Slowness, it turns out, can be its own kind of grace. And here is the thing about that slow golden world it burns. It should not be the hottest planet. It is not the closest to the Sunday. That would be Mercury, small and grey and close enough to the flame that you might expect it to hold the record. But it doesn't. Venus does. The surface of Venus sits at around 465 degrees Celsius on average, hot enough to melt lead day or night pole to pole. Mercury, despite being so much nearer to the Sun, reaches only about 430 degrees on its sunlit side, then plunges to nearly -180 at night. Venus barely flinches. What makes the difference is the sky. The thick blanket of atmosphere on Venus traps heat so completely that it never escapes, never cools, never breathes out. The planet holds everything it is given and releases nothing. Sometimes the thing that makes a place unbearable is not proximity to the source of heat, but the inability to let anything go. And as you rest right now quietly, in whatever position your body has found, consider this. The air moving gently in and out of your lungs contains molecules that have been part of this solar system since before the Earth existed. The breath you are drawing in right now connects you without drama or ceremony to something 4.5 billion years old. The oxygen you breathe was forged mostly in the cores of ancient stars released into the cosmos. When those stars ended, gathered into clouds, compressed into our sun, scattered into planets, stirred into oceans, swallowed by early life, exhaled upward through billions of years until it found its way, quietly and without fanfare, into this moment. Humans breathe roughly 22,000 times per day. Each breath is an unremarkable act and an ancient one. There is nothing you do more often and almost nothing you think about less. In that, forgetting perhaps is a kind of gift. Some things are so old, so reliable, so woven into what you are, that the body simply trusts them and lets them happen and rests. Now turn the planet gently in your mind, the way you might turn a globe on a desk, and notice something strange. Every planet in our solar system spins in roughly the same direction, the same way a top spins when you twist it with your right hand. Prograde rotation, scientists call it. It is the inherited motion of the spinning cloud of gas and dust from which everything formed. Almost all planets kept that spin. Venus did not. Venus rotates in the opposite direction, retrograde rotation, so that if you could stand on its surface and watch the sky, the sun would rise in the west and set in the east. Slowly, over the course of many Earth months. no one is entirely certain how this happened. The leading theories involve an ancient massive collision with another body early in the solar system's history, something that struck hard enough to tip the planet's rotation into reverse. But the details remain uncertain. Scientists still debate the precise mechanism. There is something quietly extraordinary about a world that moves against the grain of everything around it and does so completely, and has done so for billions of years without apology. The clouds of Venus are not the soft, white, friendly kind. From Earth, Venus looks beautiful, a steady, creamy light, brighter than anything in the night sky except the moon. Ancient peoples watched that light and named it after love, after beauty, after the most luminous goddess they could imagine. And from a distance, it earns that name. It shimmers, it holds steady, it glows. But inside those clouds there is sulfuric acid. Not in trace amounts, the clouds are composed substantially of sulfuric acid droplets, suspended in a thick atmosphere of carbon dioxide under crushing pressure. If you rose up through the Venusian atmosphere in a balloon, you would pass through layers of haze and eventually enter the cloud deck, where acid would begin to eat through almost any material we know how to make. And yet from 100 million kilometers away, those acid clouds catch the sunlight and throw it back toward Earth with such efficiency that Venus shines like a lantern hung in the dark. Beauty and danger are not always opposites. Sometimes they share the same clouds. We have already touched on the fact that Venus's day is longer than its year, measured by its slow rotation around its own axis. But there is another way to measure a day, not the slow turn of the planet itself, but the time from one sunrise to the next. And here the strangeness deepens. Because Venus orbits the Sun in the same period, it rotates the Sun, moves through the Venusian sky in a complicated drifting arc. A solar day on Venus sunrise to sunrise lasts approximately 117 Earth days, not 243. Because the planet is also moving around the Sun during that time, the two motions combine into something stranger and slower than either one alone. Imagine watching the Sun drift across a sky for nearly 4 Earth months, before it finally, slowly set. There is something in that image that is almost meditative. A world with enough time to watch every moment of light arrive, travel, and depart. Nothing rushed, nothing skipped. Some things only become beautiful when you have enough time to let them arrive. Of the 8 planets circling our Sun, 7 bear names shared with gods of all genders, gods of war, of the sea, of the harvest of the sky. Venus alone carries a goddess of love. The Romans chose the name because of how the planet looked, luminous, soft, arriving in the evening like a lantern lit early for guests. The Greeks called her Aphrodite. The Babylonians called her Ishtar, thousands of years before that. Almost every ancient culture that looked up at that bright, steady point of light reached for the same kind of word. Something feminine, something luminous. Something that arrived before the dark fully settled in. The planet itself, of course, knows nothing of names. It burns and turns and holds its poisoned clouds without caring what any small creature on a neighboring world has decided to call it. And yet the name is ours to keep a record of how humans have always done the same thing when something in the sky moved them. They reached for beauty. They reached for love. They reached for a word worth saying aloud. Venus is the only planet in our solar system named after a goddess. A name held for thousands of years is its own kind of monument. Now imagine this: you are aboard one of the toughest machines ever built by human hands. You have been engineered to survive the impossible pressure, heat acid. You descend through orange clouds into a world no living thing has ever touched. And the moment you land on the surface of Venus, you have approximately 2 hours before the planet simply unmakes you. The atmospheric pressure on the surface of Venus is about 92 times greater than Earth's at sea level equivalent, to being nearly 900 meters beneath the ocean. Every probe ever sent to Venus's surface was eventually destroyed by that pressure or the heat, or both. Even the toughest Soviet-built landers, hardened like small submarines and packed with insulation, survived only around 2 hours before going silent. There is no fragility in that. There is only an honest measure of how different a world can be from the one that made us. We built the toughest thing we knew how to build, sent it somewhere we could never go ourselves, and it did everything we asked of it, for 2 hours, and then the planet won. There is a strange kind of respect in that. We tried. Venus simply was what it was. Venus travels alone. Of all the planets in our solar system, most have company. Mars has 2 small cratered moons. Jupiter holds dozens, a whole crowded family of them, some larger than planets themselves. Even tiny distant Pluto has a moon nearly half its own size, locked in a slow, faithful orbit. But Venus has none. No moon circles it. No captured rock keeps it company in the dark. It makes its way around the sun in complete solitude, turning slowly, holding its clouds close, asking nothing of the space around it. Scientists aren't entirely certain why. The leading ideas suggest that Venus may have once had a moon formed the same way Earth's moon likely was, from a massive ancient collision, but that over billions of years gravitational interactions caused that moon to spiral inward and be absorbed back into the planet. Or perhaps the collision that reversed Venus's rotation also prevented a stable moon from ever forming. The honest answer is we don't fully know. What we do know is that Venus moves through its orbit without anything orbiting it in return. Alone and bright and entirely self-contained, there is no sadness in that. Some things simply carry their own completeness. Stand on the surface of Venus, if such a thing were possible, and look up at the sky in the direction where the sun ought to rise. You would wait. The light would gather slowly from the west. On Earth, the sun rises in the east, because our planet spins eastward the same direction it orbits. But Venus spins in the opposite direction, so its sun rises in the west and sets in the east. If you had a compass on Venus, magnetic north and geographic east would point toward the sunrise. Every instinct your body carries about morning light, about which direction dawn comes from, would be quietly, gently wrong. This is not a small thing. The direction of sunrise is one of the oldest orientations humans have. Ancient temples were built to face it. Calendars were organized around it. The word east in some languages carries inside it an ancient root meaning dawn. And on Venus, dawn comes from the other side entirely. Venus rotates from east to west, retrograde rotation, the only planet besides Uranus to do so, though Uranus is tilted on its side, which is a different kind of strangeness altogether. The universe does not always agree with our most basic assumptions about which way morning comes. Even now, as this moment passes quietly, your heart is beating in a rhythm that belongs to a lineage older than almost anything you can imagine. The human heart, your heart specifically, is the descendant of much simpler pumping structures in the earliest vertebrates. The 4-chambered heart that keeps you alive today took hundreds of millions of years to arrive at its current form, refined across fish, then amphibians, then reptiles, then the earliest mammals. Each generation inheriting something from the one before and passing it forward changed just slightly, just enough. The rhythm in your chest right now is the accumulated result of every ancestor who lived long enough to have children. You didn't choose that rhythm. It came to you already running. The average human heart beats around 100,000 times per day. In a lifetime that is roughly 3 billion beats, each one carrying on a conversation with your lungs, your blood, your brain, that began before you were born and will not stop until the very end. 3 billion is also very roughly the number of years that complex life has existed on Earth. Your heart has been practicing in its way for a very long time. Long before the space age, before telescopes, before any instrument capable of piercing the Venusian clouds, scientists looked at Venus and Earth and said, these two are almost the same. And in the ways that can be measured from a distance, they were right. Venus and Earth are remarkably close in size. Venus is about 95% the diameter of Earth and roughly 81% of its mass. They formed at the same time, from the same cloud of material, in the same region of the young solar system. For billions of years they were considered planetary twins, the most similar pair of worlds in the solar system, traveling on neighboring tracks around the same Sunday. The comparison still holds in a structural sense. Both have similar densities, similar compositions, similar internal temperatures probably. Both likely have molten cores. Both have substantial atmospheres. By the rough arithmetic of planetary formation, they should have turned out similarly. They did not. One became a world of blue oceans and breathing forests and quiet evenings. The other became something close to an oven. The same ingredients, the same kitchen, and two entirely different outcomes. Scientists are still working out exactly where the paths diverged. It is one of the most important questions in planetary science, and it does not yet have a complete answer. The surface of Venus looks, in geological terms, surprisingly new. Not new in the way a freshly paved road is new, but new in cosmic time. Most of the surface appears to have been laid down within the last 300 to 500 million years, which sounds ancient by human standards, but is relatively recent on the scale of planetary history. Earth's surface has features billions of years old. The Moon holds craters from the earliest violent period of the solar system, but Venus's surface, as best as we can tell from radar mapping, has been almost entirely reshaped within a geologically recent window. The leading explanation is something scientists call a global resurfacing event, a period when volcanic activity became so intense across the entire planet that it effectively melted and remade the surface from edge to edge. The old craters, the old mountains, the old record of what came before erased and replaced. It's as though the planet every few 100 million years simply starts over, wipes the slate, and begins again. There is something both unsettling and quietly freeing about a world that can do that holds nothing from what came before, not because it doesn't matter, but because the heat eventually gets to everything. Somewhere in the thick cloud layers above Venus there may be lightning. Not occasionally, not rarely, possibly constantly, a permanent electrical storm hidden inside clouds of acid and carbon dioxide flashing and discharging in silence, while the surface far below sits motionless in its crushing, heated dark. The evidence for Venusian lightning has been debated for decades, gathered by Soviet probes that detected what seemed like electrical signals, and more recently hinted at by European and American missions. Scientists still aren't entirely certain whether what those instruments detected was genuine lightning or some other form of electrical discharge in the atmosphere. The question remains genuinely open, but the image holds regardless a world where far above the slow and silent surface there is constant electrical energy moving through the clouds, light and heat and charge flickering in a place no human eye has ever directly seen. We know so little about what happens in those clouds. We have only measurements and theories, and the quiet admission that the universe keeps some of its most dramatic moments entirely to itself. Some storms never need an audience. In 2020, a team of scientists announced something that briefly changed the conversation about Venus entirely. They reported detecting phosphine in the upper atmosphere of Venus. Phosphine is a gas, a molecule made of one phosphorus atom and 3 hydrogen atoms, that on Earth is associated almost exclusively with either industrial processes or biological ones. It is produced by certain microorganisms living in oxygen-free environments. The detection made using radio telescopes in Hawaii and Chile suggested the presence of something in the Venusian clouds that current chemistry could not easily explain. The announcement was followed almost immediately by questions, recalculations, and debate. Other scientists revisited the data and found the signal weaker than first reported. The methodology was challenged. The numbers were revised downward. The conversation became careful and technical and unresolved. As of now, scientists still do not fully agree on whether phosphine is genuinely present in detectable amounts on Venus or what might be producing it, if it is. What remains true is this, the question was asked. The instruments were turned toward that golden light in the sky, and something unexpected came back. And the question of whether Venus's clouds could harbor some form of life, however strange, however simple, has not been fully closed. Some questions once opened are very difficult to put back. On a clear night after sunset or before sunrise, the brightest point of light in the sky that isn't the moon almost certainly belongs to Venus. It shines at a magnitude of up to -4.9, a number that means very little on its own, but which places it so far above every other planet and star in Earth's night sky that it is in a category almost by itself. It is bright enough that people sometimes call authorities to report it as a strange light in the sky. It has been mistaken for aircraft, for drones, for things that should not be there. Its steadiness, its brightness, its color, all of it conspires to make it look significant, intentional, close. Venus reflects about 70% of all the sunlight that hits it because those thick acid clouds act as an almost perfect mirror. Earth reflects only about 30%. The moon reflects even less. And so that golden point of light you may have noticed above the horizon on a clear evening, the one that seems just slightly too bright to be a star that is a world of crushing pressure and melting heat, throwing sunlight back at you with almost perfect efficiency from across an ocean of space. You are reading reflected light from a place no human has ever stood. There is a particular kind of wonder in learning that something you thought you understood was for a very long time two different things. For ancient astronomers, Babylonian, Greek, Egyptian, Chinese, Venus appeared twice in the sky, and they did not always know it was the same object. In the morning before sunrise, a brilliant point of light would climb above the eastern horizon, herald the coming day, then fade as the sun arrived. In the evening after sunset, a different brilliant light would appear in the west, hover for a time, then follow the sun below the horizon. These two lights seemed separate. They had separate names. The Greeks called the morning star Phosphorus, the light bringer, and the evening star Hesperus. It was the philosopher Pythagoras, or possibly his school, who first proposed that these two lights were the same object seen at different points in its orbit. Later, Greek astronomers confirmed it. The Babylonians may have understood this even earlier. Their astronomical records suggest they tracked Venus as a single body across both appearances with remarkable precision as early as 1600 BCE. The same light, two names, thousands of years before anyone understood why it disappeared and reappeared. Sometimes, what looks like two separate things is one thing patient enough to come back. There is a feeling that arrives when you look through a telescope for the first time and see something you did not expect. Point a modest telescope at Venus on the right night, and you will not see a featureless dot. You will see a crescent, a thin, curved sliver of light, exactly like a quarter moon or less, depending on where Venus sits in its orbit. This surprises almost everyone who sees it for the first time. Planets most people assume should look round, full, complete. But Venus shows phases, just as the moon does, because it orbits inside Earth's orbit closer to the Sunday. When Venus is on the far side of the Sun from Earth, it appears small and nearly full, fully lit but distant. When it swings around toward our side, it grows larger in apparent size but shows only a thin crescent because we are now seeing mostly its night side. The geometry is the same geometry that governs moonlight on a clear night. Venus shows phases visible through a telescope, a discovery Galileo made in 1610 and one that quietly dismantled the idea that all celestial bodies orbited the Earth. What you see depends entirely on where you are standing and where the light is coming from. Galileo Galilei pointed his telescope at Venus in the autumn of 1610, and what he saw troubled the established order of the universe. At the time, the dominant model of the cosmos placed Earth at the center of everything. The sun, the moon, the planets, the stars, all of them were understood to circle around us. It was not merely a scientific position. It was theological, philosophical. It was the shape of reality as most educated people understood it. But if Venus showed phases growing from crescent to nearly full and back again, it meant that Venus had to be orbiting the sun, not the Earth. An Earth-centered orbit could not produce the full range of phases Galileo observed. The geometry simply didn't allow it. Venus, the evidence said, went around the Sunday, and if Venus did, the model that placed Earth at the center of everything was incomplete at best. Galileo reported his observations carefully. He was not the only one working on these questions, but his telescopic evidence of Venus's phases became one of the clearest early demonstrations that the heliocentric model, the sun at the center, was correct. A crescent of light on a distant world, quietly rearranged what humans thought they knew about their place in the cosmos. Across the entire recorded history of astronomy, there are events so rare that no single human lifetime is long enough to see them twice. A transit of Venus is one of those events. It occurs when Venus passes directly between Earth and the Sun, appearing as a small dark circle moving slowly across the face of the Sun over the course of several hours. The geometry required is precise. Venus must cross the plane of Earth's orbit at just the right moment, in just the right alignment. This happens in pairs 8 years apart, and then not again for more than a century. The pattern runs in cycles of roughly 243 years, 2 transits 8 years apart, then a gap of 121.5 years, then 2 more transits 8 years apart, then a gap of 105.5 years, and so on. This rhythm, precise, mathematical, utterly indifferent to human calendars, has been unfolding since long before anyone was watching. The rarity of something does not diminish it. Sometimes it is exactly the rarity that makes it matter. The most recent transit of Venus crossed the Sun's face on June 5th and 6th, 2012. Millions of people around the world watched it through telescopes, through solar filters, through pinhole projectors made from cardboard and foil. For 6 hours and 40 minutes, a small dark circle Venus, enormous in reality, but tiny against the Sun, moved across that blazing disk in a slow, unhurried arc. No one alive today will see the next one. The following transit of Venus will occur on December 10th and 11th, 2117. The people who will watch that transit are not yet born. Their parents may not yet be born. The world they will inhabit, the instruments they will use, the languages they might speak, all of it remains entirely unknown to us. And yet the transit will happen. Venus will move. The Sun will be there. The geometry will align as it always has, without needing anyone to remember it or prepare for it. Some appointments are kept regardless of whether anyone shows up. In the 18th century, when the transit of Venus was understood to be a rare and measurable event, scientists realized it offered something precious, a way to calculate the distance from Earth to the Sunday. The method was geometric. By observing the transit from 2 widely separated points on Earth and measuring the slight difference in the path Venus appeared to take across the Sun, astronomers could calculate the distance using triangulation. It required coordinated observations from locations as far apart as possible, which meant expeditions to remote corners of the world. Captain James Cook sailed to Tahiti in 1769 specifically to observe the transit of Venus. Other expeditions went to Siberia, to Newfoundland, to the shores of Hudson Bay. Scientists endured months at sea, harsh conditions, instrument failures, clouds rolling in at the last moment, all for a few hours of observation. The results, combined and calculated, gave humanity its first reasonably accurate measure of the solar system's scale. That same impulse, the willingness to cross oceans and endure difficulty for the sake of a moment of understanding, lives in every person who has ever stayed up too late watching something beautiful cross the sky. And perhaps that impulse lives in you right now, in whatever quiet way brought you here tonight. The longing to understand something larger than the immediate moment, to let the mind wander outward past the walls and the ceiling and the atmosphere, and into the space where Venus moves its slow golden arc. That longing is not new. It is not particular to any century or culture or level of education. It is as old as the first person who looked up at a bright light in the evening sky and felt, without words for it, that it mattered. Every telescope ever built, every probe ever launched, every transit ever recorded in a leather-bound notebook by candlelight on a ship in the South Pacific, all of it begins in that same quiet place. A person, a sky, a feeling that something out there is worth paying attention to. You are part of that lineage simply by looking, simply by wondering. That is not a small thing. The Romans chose the name Venus, carefully, deliberately reaching for their most luminous goddess to match the most luminous light in their sky. But long before Rome, in the river valleys of Mesopotamia, the Babylonians watched the same light and named her Ishtar, goddess of love and war and the morning star. They tracked her movements across the sky with such precision that surviving clay tablets record 21 years of Venus observations from around 1700 BCE. These tablets, known as the Venus Tablet of Amisaduqa, are among the oldest astronomical records in human history. The Babylonians understood that Ishtar disappeared from the evening sky and reappeared in the morning sky, and they recorded the exact number of days between each disappearance and reappearance over years of careful watching. They did not know they were watching a planet. They did not need to. They watched anyway faithfully, because the rhythm of that light seemed important. It was important. It is still important. The numbers they recorded 3700 years ago have been verified by modern astronomy. Attention sustained over a long time eventually becomes knowledge. Right now, without moving from wherever you have settled, you are closer to Venus than you might imagine. Not in kilometers, the distance between Earth and Venus varies from about 38 million to 261 million kilometers, depending on where both planets sit in their orbits. But in terms of visibility, in terms of access, Venus may be above your horizon at this very moment. On many evenings and many mornings throughout the year, it is simply there. No telescope required, no special equipment, no training. Just a clear sky and a few minutes of stillness. Venus is visible to the naked eye more consistently than any other planet. It appears in the evening sky for months at a time, then disappears briefly as it passes between Earth and the Sun, then reappears in the morning sky before sunrise. This cycle repeats roughly every 19 months, with Venus spending approximately 9 to 10 months visible in the evening and a similar stretch visible before dawn. If you stepped outside tonight and looked toward the horizon where the sun recently set, or where it will rise, there is a reasonable chance that Venus is already there, waiting quietly as it has been every evening and morning of your entire life. It was there before you were born. It will be there long after. But it is also simply there tonight. Here is something worth sitting with for a moment. Venus completes one full journey around the Sun in approximately 225 Earth days. In that same span of time, Venus rotates on its own axis only once, actually slightly less than once given the 2-4-3-day rotation period. This near coincidence between the length of Venus's day and the length of its year is not fully explained. Some scientists have proposed that gravitational interactions with Earth over billions of years may have slowly nudged Venus's rotation into something close to a resonance with its orbital period, a kind of gravitational conversation between two neighboring worlds. If that resonance theory holds, then Earth and Venus have been subtly influencing each other across hundreds of millions of kilometers for billions of years, each shaping the other's rhythm in ways too slow to observe in a single lifetime, or 1,000 lifetimes. Two worlds spinning and orbiting quietly in conversation across an ocean of space, not touching, not close, but connected in the patient arithmetic of gravity in ways that neither one could have chosen. Some relationships work entirely below the threshold of awareness. High above the slow, silent surface of Venus, the clouds move fast, while the planet below turns only once every 243 Earth days. The cloud layers above race around the entire planet in just 4 Earth days. The upper atmosphere of Venus is caught in a perpetual planet-encircling storm. Wind speeds in the upper cloud deck reach around 300 to 400 kilometers per hour, fast enough to carry a weather system from one side of the planet to the other in the time it takes Earth to complete 4 ordinary rotations. This phenomenon is called superrotation, and scientists still don't fully understand what drives it. The sun's energy alone doesn't seem to account for it. Something in the interaction between the atmosphere and the slow-turning planet beneath is amplifying the wind, accelerating it far beyond what models initially predicted. It remains one of the genuinely open questions in planetary atmospheric science. So Venus holds 2 speeds at once, a surface barely moving, ancient and still, and a sky in constant rushing motion overhead. Most things contain more than one rhythm if you look carefully enough. When radar instruments aboard the Magellan spacecraft mapped Venus in the early 1990s, what came back was a portrait of a world with unexpected geography. Venus has vast highland regions, rising above its volcanic plains, regions that planetary scientists have called continents for the way they stand elevated above the surrounding lowlands. The two largest are Ishtar Terra in the north, roughly the size of Australia, and Aphrodite Terra, near the equator, larger still, closer in size to South America. These highlands were not formed the way Earth's continents were through the slow collision and drift of tectonic plates. Venus has no plate tectonics as far as we can determine. Its highland regions rose through other means, massive volcanic upwellings, crustal thickening processes that planetary scientists are still working to understand fully. Ishtar Terra sits at Venus's North Pole region and contains the planet's highest mountains. Maxwell Montes, the tallest peak on Venus, rises about 11 kilometers above the mean surface elevation. Higher, relative to its surroundings, than Mount Everest, rises above sea level on Earth. A mountain taller than Everest, on a world with no plate tectonics inside an acid cloud where the air itself would crush you. The universe is not short on ambition. Maxwell Montes rises from Ishtar Terra like something the planet decided very slowly to push upward. At roughly 11 kilometers above Venus's mean surface level, it is the highest point on a world where the lowest and highest elevations are actually closer together than Earth's range. Venus is a somewhat smoother planet overall, despite its enormous volcanic features. But Maxwell Montes is still a mountain by any human definition, a mass of ancient rock forced upward by internal forces and held there under the weight of that crushing sky. To put it in a scale that the body understands, Mount Everest, Earth's highest peak, rises about 8.8 kilometers above sea level. Maxwell Montes on Venus rises higher than that above its own reference point. If you stood at the base of Maxwell Montes on Venus and looked up assuming you could survive the pressure and the heat and the acid, the summit would be higher above you than the summit of Everest is above the sea. And the air at the top of Maxwell Montes, while still crushingly dense by Earth standards, is thin enough compared to the surface below, that the temperature there may be somewhat lower, perhaps only around 380 degrees Celsius, instead of the summit of the highest mountain on Venus is the closest thing that world has to a cool day. Now try to imagine moving through the Venusian atmosphere, not falling through it, not flying above it, but walking through it at the surface. The atmospheric pressure at Venus's surface is about 92 times that of Earth's at sea level. To experience a comparable pressure on Earth, you would need to descend nearly 900 meters below the ocean's surface. At that depth, water presses on a diver's body with enough force to be life-threatening without specialized equipment. The pressure on Venus is that great, except instead of cold seawater, the medium is superheated carbon dioxide, dense enough that walking through it would feel physically resistive, the way moving through shallow water does. The Soviet engineers who designed the Venera landers understood this. They built their probes not like aircraft or like ordinary spacecraft, but like deep-sea submersibles, thick-walled, heavily reinforced, engineered to resist being crushed from the outside in. They treated the Venusian atmosphere the way oceanographers treat the deep sea, as a medium to survive inside, not merely a void to cross. That reframing atmosphere as ocean is one of the most elegant pieces of engineering thinking in the history of space exploration. Sometimes understanding a problem differently is the same as solving it. The permanent storm at Venus's south pole is not a storm in the way a hurricane is a storm. On Earth, hurricanes form over warm ocean water, spiral outward from a central eye, and eventually dissipate when they move over land or cooler water. They are temporary. They end. But at Venus's south pole and its north, there exists a persistent atmospheric vortex, a churning, double-eyed structure that has been observed to remain stable for years. The European Space Agency's Venus Express spacecraft watched it closely between 2006 and 2014 and found it consistently present, shifting slightly in shape but never dissolving. The structure is sometimes called a double vortex because it appears to have not one central eye, but two, swirling around each other in a slow, coupled rotation at the pole. Nothing quite like it exists in Earth's atmosphere, though Earth does have polar vortexes, the one that occasionally pushes cold air southward in winter. But Earth's polar vortexes are temporary visitors. Venus's polar vortex appears to be a permanent feature of a permanent atmosphere. A storm that has been turning for longer than any human civilization has existed, over a pole no sunlight ever reaches at a useful angle, on a world no human has ever visited. Stillness and motion are not always what they appear to be. And even as you rest right now, your body is managing its own kind of stillness that is not stillness at all. Your core temperature, the temperature deep inside your torso around your liver and heart, stays remarkably constant, maintained within a narrow range by a system of feedback loops, so reliable that most people never think about it. Sweat glands activate blood vessels near the skin, dilate or constrict, breathing patterns shift subtly. Metabolism adjusts, all of it orchestrated without conscious instruction, all of it running quietly beneath whatever you are thinking about right now. The average human core temperature is approximately 37 degrees Celsius, and the body works continuously to keep it there. Venus, by contrast, maintains its surface temperature through entirely passive means, the thick blanket of its atmosphere, doing what millions of years of biological evolution built your body to do deliberately. Two very different systems arriving at the same result, a temperature held steady, a constancy maintained against the pull of the outside world. Warmth, it turns out, is something both planets and bodies know how to protect. When scientists chose a name for the largest volcano on Venus, they reached back 4,000 years to ancient Egypt. Ma'at Mons takes its name from Ma'at, the Egyptian goddess of truth, justice, and cosmic order. In Egyptian belief, Ma'at was the principle that held the universe together, the force that kept chaos from overwhelming the world. Her symbol was a feather used in the weighing of souls. She was not a god of power or destruction, but of balance of things being as they should be. It is a quietly beautiful choice for a volcano. Ma'at Mons rises approximately 8 kilometers above Venus's mean surface elevation, making it the planet's second highest peak and its largest shield volcano, a broad, gently sloping mountain built up over time by repeated lava flows rather than explosive eruptions. Recent analysis of radar data from the Magellan mission, re-examined decades later with fresh eyes, suggests that Ma'at Mons may have shown signs of active volcanic change, lava flows that appeared different between passes, hinting that eruptions may have occurred during the mission itself. A volcano, possibly still active, named for a goddess of truth, on a planet we are only beginning to understand. There is something fitting about naming a thing we cannot fully see after a principle we are still learning to practice. Ma'at Mons is not simply tall, it is vast, in the way that only shield volcanoes can be. On Earth, the largest shield volcano is Mauna Loa in Hawaii, which spreads across a base nearly 120 kilometers wide and rises gradually from the ocean floor in a long, low dome. Shield volcanoes are built differently from the steep, dramatic peaks most people picture when they think of volcanoes. They do not explode, they flow. Lava pours from their vents and spreads outward in thin sheets, traveling long distances before cooling each eruption, adding another thin layer to the growing structure beneath. Ma'at Mons follows this same patient architecture. It rises not dramatically but gradually, over what is believed to be millions of years of accumulated eruptions. And if the most recent radar analysis is correct, if there were genuine volcanic changes during the Magellan mission in the early 1990s, then Ma'at Mons may still be adding to itself, layer by layer, flow by flow. A mountain that builds itself slowly, one thin layer at a time over millions of years. There is something in that image that feels quietly like a useful thing to remember. The Soviet Venera program remains one of the most extraordinary and least celebrated achievements in the history of space exploration. Between 1961 and 1984, the Soviet Union launched 16 Venera spacecraft toward Venus. The early missions failed in various ways, lost in transit, crushed on descent parachutes that didn't deploy correctly in an atmosphere far denser than anticipated. Each failure taught the engineers something. Each rebuilt probe carried forward the lessons of the ones before it, until finally, on the 15th of December, 1970, Venera 7 became the first spacecraft to successfully land on another planet and transmit data from the surface. It survived for 23 minutes before going silent. Venera, 9 inches 1,975, sent back the first photographs from the surface of Venus, grainy orange-lit images of flat rocks and a hazy lit sky. Venera, 13 inches 1,982, survived for 127 minutes and sent back color photographs, sound recordings of the Venusian surface and soil analysis data. It remains to this day one of the most complete portraits we have of what it is actually like to be on the surface of another planet. 23 years of trying, failing, learning, rebuilding and trying again, for 127 minutes of pictures and sound from a place no human has ever been. The persistence required to build something, knowing it will be destroyed, is a particular kind of courage. The photographs sent back by the Venera landers are not beautiful in the way that photographs of Earth from space are beautiful. They show a flat, rocky plain extending in every direction, lit by an orange-yellow light filtered through the thick cloud layer above. Not the harsh brightness of direct sunlight, but something more diffuse, the way light looks under a heavy, overcast sky, except warmer in color, more amber. The rocks are flat and angular, some appearing fractured, lying on a surface that looks almost like a dried lake bed. The horizon, where visible, is close. The dense atmosphere limits visibility to perhaps a few kilometers at most. There is no wind strong enough to move anything. No tracks. No disturbance in the dust. The cameras captured a place that appeared to have been perfectly permanently still for a very long time. And yet the light is genuinely surprising. Most people imagining Venus from outside might expect total darkness under those thick clouds. But the Venera images show a world that is lit dimly, but distinctly in the way a room is lit by a single lamp behind a closed curtain. Enough to see by, enough to photograph. Enough light reaches the surface of Venus to cast a shadow, even through 60 kilometers of acid cloud. Even in the harshest places, some light finds a way through. You have been here through all of this, through the volcanoes and the vortexes and the ancient clay tablets, and the photographs sent back by machines that knew they were going to be destroyed. And perhaps you have noticed something. Perhaps you have felt somewhere in the listening that Venus keeps pulling the mind toward the same quiet question. What happened there? What tipped a world so similar to ours into something so different? The question is not merely scientific. It carries something underneath it, a wondering about thresholds, about how close a thing can come to being one thing before it becomes another entirely. Scientists believe that Venus was probably habitable, or close to habitable, for perhaps 2 billion years, early in its history, before whatever process drove its temperatures upward became irreversible. 2 billion years is longer than complex life has existed on Earth. It is an almost incomprehensible span of time during which Venus may have had liquid water, moderate temperatures, and conditions that we would today recognize as survivable. And then gradually it didn't anymore. We don't fully know why. And that not knowing carries its own kind of weight, a weight worth sitting with, not with fear, but with the seriousness it deserves. The wind at Venus's surface moves at less than 2 kilometers per hour. That is slower than most people walk. Slower than a gentle stroll along a quiet street on a still afternoon. At the surface, despite everything, despite the crushing pressure, the melting heat, the constant electrical energy in the clouds far above, the wind barely stirs. The thick, dense atmosphere near the surface moves sluggishly the way very deep water moves, more like a slow drift than anything that could be called a breeze. This means that the flat rocks photographed by the Venera landers have likely been lying in the same position, undisturbed, for an extraordinarily long time. There is no erosion by wind at the surface in any meaningful sense. No slow wearing away of edges, no movement of dust across the plain. The rocks sit where they fell or where they formed, held in place by gravity and surrounded by nearly still air. The stillness of the surface is profound. It is the kind of stillness that belongs not to absence, but to wait, the stillness of something so dense and so pressured that motion becomes almost impossible. That quality of stillness, heavy, warm, complete, is something the body understands, perhaps at the edge of sleep. Your body knows that stillness well. Right now, if you are settling toward sleep, your nervous system is doing something that took hundreds of millions of years to develop. As wakefulness gives way, the brain's electrical activity shifts from the fast, jagged rhythms of conscious thought towards slower, larger waves. Heart rate drops. Breathing slows and deepens. The small muscles around the eyes relax. The sense of the body's edges becomes less distinct. The boundary between self and surface softens. This transition is managed by structures deep in the brain that predate the human species by an enormous margin. The hypothalamus, the thalamus, the brainstem, these are ancient structures inherited from ancestors who look nothing like us, refined over geological time into something that now quietly every night returns you to a state of rest. Sleep is not an absence of the body. It is the body doing something ancient and necessary and deeply its own. Every time you fall asleep, you are doing something your ancestors have been doing for more than 500 million years. That continuity held inside you without effort is one of the quietest forms of belonging there is. The clouds of Venus contain water. Not much, and not in a form that would comfort anyone hoping for rivers or rain, but water vapor and water-containing droplets exist within the Venusian cloud layers, mixed into the sulfuric acid and carbon dioxide that make those clouds so hostile. The water that remains is bound up in chemical reactions incorporated into the acid droplets present but unavailable. The way water locked in certain minerals on Earth is real but unreachable. Scientists believe that early Venus may have had vastly more water, possibly even oceans. The evidence for this lies partly in the ratio of different forms of hydrogen detected in the Venusian atmosphere today. The current atmosphere shows a high ratio of deuterium to ordinary hydrogen, a signature that suggests enormous amounts of water were once present and have since escaped into space, with the heavier deuterium atoms left behind in proportionally greater numbers like sediment after a flood. Venus may have lost its oceans not in a single catastrophic event, but slowly over hundreds of millions of years, as water molecules were broken apart by solar ultraviolet radiation and the hydrogen drifted away into space. An ocean patient and ancient undone one molecule at a time over millions of years. Some losses happen so slowly that they are invisible until they are complete. More than 3,000 years ago, in the cities that lined the rivers of Mesopotamia, there were people whose entire profession was watching the sky. They were not astronomers in the modern sense. They did not have telescopes or mathematical models of planetary motion or any concept of gravity. What they had was time and patience and clay. They pressed their observations into wet clay tablets, with reed styluses recording the rising and setting of Venus, with a consistency that spanned generations. The Venus tablet of Amisaduqa, discovered in the ruins of Nineveh and dated to around 1600 BCE, records 21 years of Venus observations, its first and last appearances in the morning and evening sky, the gaps between disappearances, the patterns that repeated, with reassuring regularity. These records were not made for science. They were made for divination, to read the sky for signs that might guide kings and armies and harvests. But the method required genuine accuracy. A wrong observation was a useless one. And so the Babylonian sky watchers watched carefully, recorded faithfully, and produced something that modern astronomers have been able to verify as remarkably precise. A discipline undertaken for one reason can produce knowledge that outlasts its original purpose by millennia. What you attend to carefully, regardless of why you began, eventually becomes something real. There is a particular geometry to Venus that makes it behave differently from the outer planets, Mars, Jupiter, Saturn, in a way that most people never think about. Venus orbits the Sun inside Earth's orbit. This means that from our perspective, Venus never wanders far from the Sun in the sky. It is always found relatively close to the horizon, either rising before the Sun in the morning or setting after it in the evening. It never appears high overhead at midnight the way Mars sometimes does. It never rises in the east as the Sun sets in the west, reaching its highest point in the middle of the night. This constraint is why ancient astronomers saw Venus as a creature of the twilight, always near the Sun, always at the edge of day and night, never fully belonging to the dark sky or the bright one. Through a telescope, this inner orbit is what produces the phases Galileo observed. As Venus moves around its orbit relative to Earth, the angle of illumination changes exactly the way the Moon's changes. When Venus is on the far side of the Sun, it appears small and nearly full. When it swings close to Earth, it becomes a large, thin crescent. The same light-changing shape depending on where you stand and where the source is and how far around the curve you are. In the autumn of 1610, Galileo wrote down his observations of Venus in an anagram, a scrambled string of letters, and sent it to fellow astronomers across Europe. This was a common practice at the time, a way of establishing priority for a discovery without fully revealing it. If someone else announced the same finding later, you could unscramble your anagram and prove you had known first. It was science conducted with the caution of a world where ideas had consequences, where the wrong observation published too boldly could bring serious trouble. The anagram unscrambled read, "The Mother of Loves emulates the figures of Cynthia," a poetic way of saying that Venus, like the Moon, shows phases. Galileo sat on this discovery for months before publishing it clearly. What he had seen was undeniable. Venus showed a full range of phases from crescent to nearly full and back that could only be explained if Venus orbited the Sunday. Not the Earth, the Sunday. He knew what it meant. He was careful about saying it plainly. And eventually the evidence was simply too clear to obscure. The truth does not always announce itself boldly. Sometimes it arrives in an anagram waiting for the right moment to be read aloud. Some things are so rare that the word rare doesn't quite carry enough weight. A transit of Venus. Venus crossing the face of the Sun, as seen from Earth, happens in pairs, separated by 8 years, and then not again for more than a century. Within any given 2, 4, 3-year cycle, there are exactly 2 transits. Most human lifetimes contain 0. A few, by fortunate timing, contain 1. The French astronomer Alexis Bouvard, born in 1767, saw the 1769 transit as a young child, or at least lived during it. He died in 1843, long before the next pair, in 1874 and 1882. The astronomer Edmund Halley of comet fame calculated the usefulness of transits for measuring the solar system, but died in 1742, knowing he would never see one himself. He wrote instructions for future astronomers, passing his method forward, like a letter addressed to people not yet born. There is something in that gesture, careful instructions written for strangers, across time, that is both humble and generous. An acknowledgement that some things are larger than one lifetime, and that the work of understanding them belongs to more than one generation. Some projects are simply too long for any single person to finish alone. The 1769 transit of Venus sent Captain James Cook to the other side of the world. The Royal Society of London organized an expedition to the Pacific to observe the transit from a location far enough from Europe to make the triangulation calculations useful. Cook was chosen to command the voyage. He sailed to Tahiti, where on June 3, 1769, a team of observers watched Venus trace its dark path across the Sun's face over the course of nearly 6 hours. The observation was complicated by something called the black drop effect, a visual phenomenon where Venus appeared to briefly connect to the edge of the Sun, making the precise moment of contact difficult to time accurately. This same effect had frustrated observers in 1761 and would frustrate them again in 1874 and 1882. The measurements from 1769 allowed a calculation of the Earth-Sun distance, but with less precision than hoped, partly because of the black drop problem. The distance Cook helped measure is now called an astronomical unit, approximately 150 million kilometers. Every distance in the solar system, every scale of planetary space, is ultimately expressed in multiples or fractions of that number. A value derived from a long sea voyage, a small dark circle, and a timing problem that no one could quite solve. The Mayan civilization of Mesoamerica built one of the most sophisticated astronomical traditions in human history, and at the center of it, alongside the sun and moon, was Venus. The Dresden Codex, one of only 4 surviving Mayan books written on bark paper and dated to around the 11th or 12th century CE, contains detailed astronomical tables tracking the synodic cycle of Venus with extraordinary precision. The Mayan astronomers knew that Venus completes its cycle relative to Earth, disappearing and reappearing as morning and evening star in approximately 584 days. They also knew that 5 of these Venus cycles equal almost exactly 8 Earth years, allowing them to predict Venus's behavior far into the future. This 584-day cycle was woven into the Mayan calendar system and used to plan religious ceremonies, agricultural activities, and military campaigns. The first appearance of Venus as morning star was considered particularly significant, a moment associated with the feathered serpent deity Quetzalcoatl, whose movements through the sky were believed to influence events on Earth. These were not guesses. They were the result of generations of careful, systematic observation, recorded and refined across centuries by people who understood that the sky followed rules, even if the names they gave those rules were different from ours. Different names, the same patient watching. And in that patient watching across every culture that ever noticed Venus, Babylonian, Greek, Roman, Mayan, Chinese, Indian, Egyptian, there is something that connects you right now in this moment to all of them. Every person who ever watched that bright light in the evening sky and felt the pull of wondering what is it, how far, what does it mean, was doing the same thing you are doing right now in whatever way brought you to this place tonight. The wondering is not new. The belonging to a species that looks up and asks questions is not new. You are not a late arrival to this. You are part of a lineage that stretches back, before writing, before cities, before agriculture, all the way to the first human eyes that tracked something bright, moving steadily against the fixed stars and felt that it mattered. That wondering is not small. It is one of the oldest and most persistent things our species does, and it costs nothing and requires nothing, and is available to anyone willing to look up. The sky has always been free to look at. When the Romans named the planet after their goddess of love and beauty, they were responding to something real. Venus, seen from Earth, is genuinely beautiful. Not in a way that requires knowledge or context, in a way that is immediately viscerally apparent to anyone who looks at it. It doesn't flicker the way stars do. It holds steady with a warm, creamy quality to its light that is softer than the blue-white of the brightest stars. In the right conditions, just after sunset or just before sunrise, when the sky is a deep blue and the horizon still carries some of the warmth of day, Venus seems to almost float, a small lamp hung in the transition between light and dark. Ancient people named it after love, partly because of when it appears. The evening star arrives as the day winds down, as people gather for the evening meal, as the pace of the day softens. The morning star appears before the work of the day begins, in the quiet before the household stirs. Both appearances are liminal threshold moments, transitions, the spaces between states. Venus was named after love, partly because love too is a kind of threshold, a place between one thing and another, a brightness that arrives at the edge of the day. The planet itself, of course, burns at 465 degrees and would dissolve you in moments. But the light is genuinely beautiful. The Mayan relationship with Venus was not simply astronomical. It was intimate in the way that only things you depend on can be. The Dresden Codex's Venus tables were not records kept out of curiosity. They were operational documents, used the way a ship captain uses tide charts or a farmer uses a planting almanac. The first appearance of Venus as the morning star was considered a dangerous moment, a time when malevolent influences streamed down from the sky along with the planet's light. Certain activities were suspended. Certain people, including in some accounts kings, were considered vulnerable. To protect against this Mayan, astronomers developed what amounted to a forecasting system. By knowing exactly when Venus would reappear, they could prepare rituals, adjust schedules, and take whatever precautions their tradition prescribed. The knowledge was protective. It was also in its way a form of respect, an acknowledgement that the sky had rhythms, and that those rhythms affected life on the ground, and that the wise response was to pay attention. The Mayan Venus tables are accurate to within a day, over a span of 481 years. Not a guess, not an approximation. A calendar of a neighboring world built by hand over centuries on bark paper, without telescopes or computers, or anything except sustained faithful watching. Some knowledge is simply the reward for paying attention long enough. Now, leave the ancient world for a moment and step into the imagination of the early 20th century. Before any spacecraft had gone anywhere, before radar had mapped a single centimeter of Venus's surface, before the Soviet probes had transmitted their first signals through those clouds, humans had to imagine what Venus was like. And because the clouds were impenetrable to optical telescopes, and because Venus was known to be close in size to Earth and somewhat closer to the Sun, the imagining went in a particular direction. Warm, wet, lush. Science fiction writers and some scientists of the early 1900s pictured Venus as a kind of primordial Earth, covered in dense jungle watered by warm seas, perhaps home to creatures that had not yet had time to become intelligent. The image was seductive because it was plausible. Nothing ruled it out. The clouds kept their secret, and into that silence, human imagination poured its own most hopeful version of what might be hiding. Ray Bradbury wrote about the endless Venusian rain. Edgar Rice Burroughs sent adventurers there. C.S. Lewis imagined it as a kind of paradise, an unfallen world covered in floating islands on a global ocean. All of it was wrong. All of it was also, in its way, a record of what humans hoped a neighboring world might be. And hope, even when it is corrected by fact, tells you something true about the people who felt it. And then the spacecraft arrived, and the imagining stopped, and what replaced it was stranger and in some ways more interesting. The first successful flyby of Venus was made by NASA's Mariner, 2 inches December, 1962. It passed within about 34,800 kilometers of Venus and measured something that settled the question of the warm jungle world. The surface temperature was not mild. It was not warm. It was close to 425 degrees Celsius, according to those first measurements, later refined to the now accepted figure of around 465 degrees. The jungle was gone. The ocean was gone. The adventurers and the floating islands and the Venusian creatures, all of it erased in a single flyby, replaced by a number that meant nothing we recognize as life could survive there. It must have been a particular kind of quiet that followed. The kind that comes when a cherished possibility is replaced by a fact. But the fact once absorbed opened new questions. Why is it that hot? How did it get that way? Could it have been different? Was it ever? The end of one imagination is always the beginning of another. Here is something the body carries that connects to all of this quietly and without announcement. Your skin is a record of adaptation. The outer layer, the epidermis, replaces itself completely roughly every 2 to 4 weeks. The deeper layers turn over more slowly, but they turn over. What feels like the same surface you have always had is actually a continuously renewed structure, built and rebuilt from materials drawn from food and water and air, maintained by systems so automatic that they operate without any instruction from conscious thought. The average human sheds somewhere between 30,000 and 40,000 skin cells per hour. Over a lifetime, the outer layer of the body is remade thousands of times. You are not the same physical surface you were a month ago. The atoms have changed. The cells have changed. What persists is the pattern, the instructions encoded in DNA that tell each new cell what shape to take, what protein to make, what role to play. Identity, it seems, is not what stays. It is what keeps being faithfully remade. Venus remakes its surface through volcanic catastrophe every few 100 million years. The human body remakes its surface quietly every few weeks without drama or fanfare. Both are still somehow recognizably themselves. Venus has a magnetic field, but it is almost too faint to find. Earth's magnetic field is generated by the movement of molten iron in its outer core, a dynamo, producing a field strong enough to deflect the charged particles of the solar wind, strong enough to make compass needles turn strong enough, to paint the sky with auroras at the poles. This field is one of the reasons Earth remains habitable. It shields the atmosphere from being slowly stripped away by the constant pressure of the solar wind. Venus, so similar to Earth in size and composition, should have something similar, but it doesn't. Its magnetic field is vanishingly weak, perhaps 100 times weaker than Earth's, possibly generated not by an internal dynamo, but by the interaction between the solar wind and the upper atmosphere. Why? Scientists aren't certain. One possibility is that Venus's slow rotation doesn't generate enough churning motion in the core to sustain a strong dynamo. Another is that Venus's interior has cooled or solidified in a way that Earth's hasn't. The question remains genuinely open. What is clear is that without that magnetic shield, the solar wind interacts directly with the Venusian upper atmosphere, gradually stripping particles away, including, over billions of years, the hydrogen that once made up its water. The absence of a shield sustained long enough can undo an ocean. Earth's magnetic field is not simply a physical feature of the planet. It is, in a very real sense, a precondition for almost everything alive on it. Without the magnetosphere, the bubble of magnetic influence that surrounds Earth, the solar wind would bombard the surface with radiation levels that most life as we know it could not tolerate. The atmosphere would slowly erode. The ozone layer, which depends partly on the atmosphere remaining intact, would thin. The surface of the planet would become increasingly hostile to biology. Mars lost its magnetic field billions of years ago, and Mars lost most of its atmosphere in the time that followed. Today, Mars has an atmosphere about 100 times thinner than Earth's, a surface scoured by radiation, and no liquid water on its surface. The connection between magnetic field and habitability is not theoretical. Mars is the example. Venus has essentially no protective magnetic field and is losing its atmosphere slowly, though Venus's dense atmosphere is so thick that it will take an extraordinarily long time to erode significantly. The invisible forces are often the most important ones. The things you cannot see or feel may be the things that make everything else possible. There is a place in the Venusian atmosphere about 50 to 60 kilometers above the surface, where the conditions are closer to Earth's surface than anywhere else in the solar system outside of Earth itself. The pressure at that altitude is roughly equivalent to Earth's at sea level. The temperature, while still warm, falls into a range between about 0 and 50 degrees Celsius, survivable in principle for certain forms of life and certain human-made structures. The atmosphere at that altitude, while still rich in carbon dioxide and laced with sulfuric acid clouds, is dense enough to provide some shielding from radiation. This is the zone that has prompted some scientists, mostly in theoretical papers at this stage, to propose that the upper atmosphere of Venus might be the most accessible place in the solar system aside from Earth for some form of biology to exist. Not on the surface, never on the surface, but floating perhaps in the clouds. Microbial life in Earth's atmosphere has been found at altitudes of up to 40 kilometers. The upper clouds of Venus occupy a similar altitude range. No evidence of life has been found in the Venusian atmosphere, but the question of whether those clouds are entirely sterile is genuinely and technically still open. Some of the most interesting places are the ones that seem on first inspection entirely impossible. And from that impossibly hostile place, humans have imagined something remarkable. In the 1970s, Soviet engineers sketched preliminary designs for what they called a Venusian aerostat, a floating platform that would drift through the upper atmosphere of Venus rather than attempting to land on its surface. NASA scientists have revisited this concept in more recent decades under the name HAVOC, High Altitude Venus Operational Concept. a proposal for crewed or uncrewed airships that would float in the temperate cloud layer roughly 50 kilometers above the surface. An airship floating in the clouds of Venus, not touching the surface, not needing to, simply drifting through the one zone of that world where conditions are almost manageable, doing science from the sky. The concept remains theoretical. No such mission has been approved or funded at this stage. But the fact that it is technically conceivable that the physics actually work, that the zone exists, that human ingenuity has found the one livable layer of an otherwise lethal world and thought we could float there, says something about what humans do when they encounter a closed door. They look for the window, and sometimes high enough up there is one. Somewhere beneath those clouds, beneath the crushing pressure and the silent volcanic plains, Venus may be carrying a memory of water. Scientists believe that early Venus, in its first billion years or so, may have had liquid water on its surface. Not a certainty, not a proven fact, but a possibility supported by climate models, by the chemistry of the current atmosphere, and by what we understand about how planets form and cool. The early sun was dimmer than it is today, which means Venus received less heat. The planet's surface may have been cool enough for long enough for water to condense and pool. Some models suggest Venus could have maintained surface oceans for as long as 2 billion years. 2 billion years is longer than it took for complex multicellular life to evolve on Earth after the first simple cells appeared. It is time enough in principle for something to begin. Whether anything did begin on early Venus, whether any molecule crossed the threshold from chemistry into biology in those ancient oceans, is something we cannot currently answer. The evidence, if it ever existed, has been erased by the volcanic resurfacing events that remade the planet's crust. A world that may have held oceans and life's possibility and lost both so completely that even the memory is gone. The universe keeps some of its most important secrets beneath layers of lava. Something changed on Venus. Something tipped it from a world that might have been habitable into the world it is now, and scientists have been trying to understand that transition for decades. The leading hypothesis involves a runaway greenhouse effect, a feedback loop in which rising temperatures caused more water to evaporate into the atmosphere, which trapped more heat, which caused more evaporation, which trapped more heat, in a cycle that could not reverse itself once it began. As the temperature rose, the oceans would have slowly evaporated. The water vapor, now in the atmosphere, would have been broken apart by solar ultraviolet radiation, with the hydrogen escaping into space and the oxygen combining with surface rocks. The trigger for this runaway effect is not fully agreed upon. It may have been a gradual increase in solar luminosity as the sun aged and brightened. It may have been a period of intense volcanic activity that flooded the atmosphere with carbon dioxide. It may have been some combination of both, reinforcing each other across millions of years. What is agreed upon is that, at some point, the process became self-sustaining. The heat produced more warming, and the warming produced more heat, and there was nothing in Venus's system to interrupt the loop. A threshold once crossed that could not be uncrossed. A slow tipping that took millions of years and could not be undone in millions more. The story of what happened to Venus is not merely a story about a planet. It is, in the most careful and precise scientific sense, a reference point, a data point, in the larger question of how common habitable worlds might be and how fragile habitability might be once it is established. Earth and Venus started nearly identically. One remained habitable, one did not. Understanding exactly why is not an abstract academic question. It is, in a very direct way, a question about what conditions are required for a world like ours to stay the way it is. The study of Venus's climate history is one of the reasons climate science on Earth has the models it does. Early Venus researchers contributed directly to the development of the greenhouse effect models used to study Earth's own atmosphere. The two planets are, in this sense, still in conversation, still teaching each other things, still connected by the fact that they ran the same experiment and got different results. Venus is not a warning in the dramatic sense. It is not a prediction. but it is quietly and seriously an example of what a small difference held for long enough, amplified by enough feedback, can become. Small differences held patiently become worlds apart. And right now, even as this settles gently into wherever your mind is resting, your body is running its own version of a feedback system. When you are anxious, your breathing tends to shorten and quicken. Shorter, quicker breathing reduces carbon dioxide in the blood. That reduction triggers physiological responses that can increase the sensation of anxiety. The anxiety produces more quick breathing. The loop can sustain itself without any new external input, the body's own chemistry amplifying a signal that the mind sent first. But the loop can also be interrupted. Deliberately slowing the breath, extending the exhale in particular, raises carbon dioxide slightly, activates the parasympathetic nervous system, and begins to ease the cycle back toward calm. The exhale is longer than the inhale when the body feels safe. You may have noticed that already tonight, as this voice has settled in, as the warmth of these words has done what warmth does. A feedback loop like the one that transformed Venus works in both directions. The same mechanism that can tip a system toward extremity can, under the right conditions, tip it back toward balance. What you breathe into the air around you tonight returns to you changed. Venus spins so slowly, and its atmosphere traps heat so completely that the temperature on its surface barely varies, from equator to pole, from dayside to nightside. On Earth, temperature differences drive almost everything. The temperature gradient between the equator and the poles drives the jet stream, the trade winds, the ocean currents, the monsoons, the entire circulation of the atmosphere that distributes heat, moisture, and nutrients around the planet. Life in almost every biome is shaped by the temperature differences between places and seasons. On Venus, that gradient is almost absent. The surface temperature at the North Pole is not meaningfully different from the surface temperature at the equator. The night side is not meaningfully cooler than the day side, despite the day side receiving direct sunlight for months at a time. The thick atmosphere is so efficient at redistributing heat and at trapping it that the planet reaches a kind of thermal equilibrium that Earth never has. Everything everywhere is approximately the same temperature. There is a kind of enforced sameness to that which feels from a distance almost peaceful and up close absolutely lethal. Uniformity and stability are not always the same thing. The thick clouds that make Venus so reflective and so hot have one more property worth dwelling on. From Earth, Venus is visible and beautiful precisely because those clouds exist. Without them, if Venus were a bare rock like Mercury, it would reflect far less sunlight and appear much dimmer in our sky. It might still be visible to the naked eye, but it would not be the brilliant, warm lamp that has drawn human attention since before recorded history. The very feature that makes Venus lethal on the inside is what makes it luminous from the outside. The clouds of Venus reflect approximately 70% of the sunlight that strikes them. Earth reflects about 30%. A bare, rocky Venus would reflect perhaps 10 to 15% comparable to the Moon's reflectivity. Venus would be several times dimmer than it currently appears. Without the acid clouds, there is no evening star. Without the poison sky, there is no gentle lamp above the horizon. The beauty depends entirely on the mechanism of the catastrophe. This is not a metaphor. It is simply what is true about Venus. But it is hard to encounter it and not feel something quiet and complicated settle in the chest. The Venera probes descending through the Venusian cloud layers pass through distinct regions on the way down. Above the main cloud deck, the atmosphere is relatively thin, and cold temperatures there can drop to around -40 degrees Celsius colder than most places on Earth's surface ever reach. This upper region is where the fastest winds blow, where the super-rotating cloud layers race around the planet in 4 Earth days. The probes fell through this zone quickly, instruments recording pressure and temperature and composition as they descended. Then the main cloud deck thick layered the sulfuric acid droplets dense enough to reduce visibility dramatically. Below that, a clearer region, still hot and pressured, but less obscured. And finally, below the clouds entirely, the lower atmosphere, a dense, orange-lit column of nearly pure carbon dioxide pressing down with the weight of nearly a kilometer of ocean water. The probes passed through all of this in less than an hour on the way to the surface. Each layer was a different world. Each one would have been lethal to any unprotected living thing, and yet the data came through. Each instrument reading was transmitted. The layers were recorded, characterized, understood a little better. We know the inside of Venus's atmosphere because machines fell through it, faithfully measuring as they went, until the heat and the pressure finally stopped them. Some knowledge is gathered only on the way down, and the sun seen from somewhere within those clouds would be a strange and muted thing, not the sharp, brilliant disk that rises over Earth's horizon on a clear morning, not the white gold circle that makes you look away. From within the Venusian cloud layers, the sun would be invisible as a distinct object, its light diffused through 60 kilometers of acid haze into a general brightening of the sky. A sourceless glow coming from the direction of the sun without revealing the sun itself. The light that reaches the surface, that orange-amber illumination captured in the Venera photographs, is what remains after passing through all of that. It is sunlight filtered into something unrecognizable, arriving at the ground without direction, without shadow, in the conventional sense, filling the space between the rocks with a warm, diffuse glow. Sunlight transformed beyond recognition by the thing it passes through still arrives, still illuminates, still makes the surface of another world visible to instruments built by people on a neighboring planet who wanted more than almost anything to see. Light finds a way, even through 60 kilometers of acid, even through almost anything if the source is bright enough. There is a kind of warmth that persists long after its source has moved on. A kind word spoken once in the right moment can be remembered for a decade. The encouragement of a single person, offered without expectation, can shape the direction of an entire life. The heat does not have to be sustained to leave something lasting behind. It only has to arrive at the right moment, when the person receiving it is open enough to let it in. This is not a scientific fact about Venus. It is something the mind reaches toward when it sits with the image of a planet that holds its heat so completely that nothing escapes. Venus cannot release what it has been given. The warmth it received billions of years ago is still there, still circulating, still trapped beneath those clouds. The Venusian atmosphere retains heat with an efficiency that no human-made insulating material approaches. The specific combination of carbon dioxide density, cloud cover, and atmospheric pressure creates a thermal trap of almost perfect completeness. What you hold with that much care stays in a way that nothing casually held ever could. There is no instruction in that. Only the image offered gently for whatever the mind chooses to do with it. The Soviet Venera program, which spanned more than 2 decades and launched 16 spacecraft toward Venus, was one of the longest sustained efforts in the history of robotic exploration. It began in 1961, the same year Yuri Gagarin became the first human in space, and it continued through a period of extraordinary technological development, political tension, scientific ambition, and repeated failure. The early missions were lost entirely, some to launch failures, some to the vacuum of space when pressurization systems failed, some crushed by an atmosphere that turned out to be far denser than expected. Each failure was analyzed. Each rebuilt probe carried forward what the previous one had taught. The program was not glamorous in the way the Apollo missions were glamorous. There were no televised countdowns watched by hundreds of millions. The successes came quietly announced in scientific papers celebrated in research institutes rather than in public squares. And yet Venera, 9 inches October 1975, sent back the first photograph ever taken from the surface of another planet. Not the moon, another planet entirely. A rocky orange-lit plain, flat stones, a horizon, the first visual confirmation of what another world's ground actually looks like seen from standing height. The first photograph taken on another planet's surface, sent by a machine that survived for 53 minutes. Some achievements are enormous and arrive without fanfare. Those first surface photographs from Venera 9 showed something unexpected. The rocks were sharp-edged. On Earth, rocks exposed to wind and water become rounded over time. Erosion softens edges, fills cracks, smooths surfaces. The older and more exposed a rock is, the more rounded and worn it tends to become. This is one of the ways geologists read the history of a landscape, by the shape of its stones. The rocks in the Venera 9 images were not rounded. They were angular, with sharp edges and flat faces, as though they had broken recently and not been weathered since. This told scientists something important at the surface of Venus, the kind of erosion that shapes Earth's rocks. Wind-driven abrasion, water flow, is almost entirely absent. The wind barely moves, there is no water. The rocks break, fall, and then simply sit where they land, edges intact, for what may be millions of years. Time passes on Venus's surface, a great deal of it, but it leaves the rocks almost unchanged. There is a kind of stillness in that which goes beyond quietness. It is the stillness of a place where the usual forces of change are absent, where what falls stays fallen, where nothing rounds anything off. A landscape with no gentle wearing away. Everything exactly as it broke. 3 new missions to Venus are in development, representing the most sustained international attention Venus has received in a generation. NASA has approved 2 missions. Da Vinci, which will send a probe diving through the Venusian atmosphere, sampling its chemistry on the way down, and photographing the highland terrain of Aphrodite Terra as it descends. And Veritas, an orbiter that will map the surface of Venus in far greater detail than the Magellan mission managed in the early 1990s. Looking for signs of current volcanic activity and tectonic processes, the European Space Agency's Envision mission will also orbit Venus, combining radar mapping with atmospheric sounding to build the most complete picture of the planet ever assembled. All 3 missions are planned for the 2030s. Together, they represent a return to Venus after decades of relative neglect, a recognition that the planet closest to Earth, the one most similar in size, the one that may once have been habitable, still holds questions that matter enormously to our understanding of how planets work and how life finds its footholds. Venus waited. It did not need our attention to continue being what it is, but our attention is returning, and what it finds may change how we understand our own world. Every spacecraft ever sent to Venus carries, in some sense, the accumulated wondering of everyone who ever looked at that light above the horizon and felt something. The engineers who designed the Venera probes were scientists, yes, but they were also people who had looked up. The mathematicians who calculated the transit observations in the 18th century were scholars, but they were also people who had once, as children, noticed something bright and asked what it was. The Babylonian scribes pressing clay tablets with records of Venus's risings were functionaries of a religious system, but they were also people who had stood in the night air and felt the pull of something larger than themselves. Every instrument, every calculation, every mission plan is downstream of that original impulse. The wondering came first. The methodology came later, in service of the wondering. You do not need to be a scientist to participate in this. The wondering is the participation. It has always been the participation. The instruments are built by humans, but the impulse that builds them is older than any institution, any discipline, any civilization. It is as old as the first clear night. The phosphine question, whether a gas associated on Earth with biological processes exists in the Venusian clouds, has not been resolved and may not be for some years. The initial 2020 announcement was followed by a period of intense scientific scrutiny. Other teams reanalyzed the telescope data and found the signal significantly weaker than first reported. Some argued that sulfur dioxide, a gas common in Venus's atmosphere from volcanic activity, might have been misidentified. The original team revised their figures downward but maintained that some phosphine signal was present. The debate continues in peer-reviewed literature, in conference presentations, in careful back and forth between teams, using different instruments and different analytical methods. This is what science looks like from the inside. Not a clean announcement followed by settled certainty, but a long, careful, sometimes contentious process of checking, rechecking, and honest disagreement. What everyone agrees on is this: if phosphine is genuinely present in the Venusian clouds, in amounts that cannot be explained by known chemical processes. That would be one of the most significant discoveries in the history of science. And if it turns out to be a measurement artifact or a misidentification, that too is a useful result, a refinement of what the instruments can and cannot detect. Either way, the question was worth asking. The instruments were worth pointing at the sky. Honest uncertainty is not a failure of knowledge. It is knowledge in its most careful form. Each of the 3 upcoming Venus missions will answer some questions and almost certainly generate new ones. Da Vinci's atmospheric probe will sample the deep atmosphere of Venus directly, for the first time in decades, looking for trace gases, measuring temperature and pressure with modern precision, and imaging the Alpha Reggio highland terrain below as it descends. Scientists hope to find chemical signatures that can help distinguish between different hypotheses about Venus's history, particularly whether it ever had surface water and what the deep atmosphere can tell us about how the planet evolved. Veritas will produce a surface map of Venus detailed enough to identify relatively recent geological features, fresh lava flows, fault lines, volcanic structures that may be geologically active. If Ma'at Mons, or any other Venusian volcano, is currently erupting, Veritas may be the mission that confirms it definitively. Envision will bridge the gap between surface and atmosphere, looking at how the 2 systems interact and seeking to understand Venus as a whole system rather than as a collection of separate mysteries. 3 perspectives on one world. 3 sets of instruments asking the same underlying question in 3 different languages. What happened to you, Venus, and could it happen to us? And somewhere above all of this, above the planning and the peer review and the mission timelines and the careful scientific uncertainty, Venus continues its slow golden circuit around the Sun, entirely unaware of being studied. It does not know about the Babylonian tablets. It does not know about Galileo's anagram, or Cook's voyage to Tahiti, or the Venera engineers who stayed late rebuilding probes that kept being destroyed. It does not know about the telescope in Hawaii that detected phosphine, or the debate that followed, or the 3 spacecraft being assembled right now in clean rooms on a neighboring world. Venus simply moves. It turns slowly against its own instinct. It holds its heat. It keeps its clouds. It throws sunlight back toward Earth with near-perfect efficiency, arriving in the eyes of whoever happens to be looking at the right moment. It does not need to know it is being watched to be worth watching. Most beautiful things don't. Every mission carries something more than instruments and calculations. When an engineer spends years of their life designing a probe, checking tolerances, running simulations, losing sleep over a heat shield that needs to survive entry into an atmosphere of crushing pressure and acid, they are doing something that is technically precise and also deeply human. They are placing a piece of careful attention into a machine and sending it somewhere they can never go themselves. They are extending the reach of human curiosity across a distance that the body cannot cross. The Venera probes carried Soviet flags pressed into the insulation. The Pioneer Venus multiprobe carried a small plaque. Every mission carries in its way some acknowledgement that it was made by people who wanted to know something and believed that knowing it mattered. The Venus missions planned for the 2030s will carry modern instruments built by teams of people who have spent careers thinking about one planet, its clouds, its chemistry, its history, its silences. Their accumulated wondering converted into hardware will cross the space between 2 worlds and begin transmitting. Every transmission is, in the most literal sense, a message from the human impulse to understand, arriving at a place no human has ever been. That impulse does not diminish with distance. It becomes, if anything, more concentrated the further it travels. The word phosphine sounds almost gentle for something so consequential. It is a small molecule, 1 phosphorus atom bonded to 3 hydrogen atoms, abbreviated as pH3. On Earth, it is produced in certain anaerobic environments, the digestive systems of some animals, the sediment of marshes and swamps, the metabolic processes of certain microorganisms that live where there is no oxygen. It has a faint smell reportedly similar to garlic or decaying fish. though most people have never encountered it in sufficient concentration to notice. In the context of Venus, the word arrived in a scientific paper in September 2020 and briefly changed the conversation about the entire planet. Not because phosphine was definitively found, the subsequent debate has been careful and unresolved, but because the question of its presence forced scientists to seriously consider what chemical processes could produce it in the Venusian clouds, and whether any of those processes might be biological. The word itself carries none of this weight when you first encounter it. Phosphine. It sounds like something a pharmacist might mention, or the name of a mineral, and yet it sits at the center of one of the most genuinely open questions in contemporary planetary science. Sometimes the most important questions arrive in the quietest language. Scientists do not yet know whether Venus formed with plate tectonics and lost them, or whether it never had them at all. On Earth, plate tectonics, the slow movement of the crust in large interlocking sections driven by heat rising from the interior, is responsible for an enormous range of processes. It recycles carbon dioxide from the atmosphere back into the mantle through subduction. It builds mountains. It drives the carbon cycle that helps regulate Earth's long-term temperature. Some scientists believe that plate tectonics may be a necessary condition for long-term planetary habitability, because without it, the mechanism for removing excess carbon dioxide from the atmosphere breaks down. Venus has no detectable plate tectonics. Its crust appears to be a single, unbroken shell, what planetary scientists call a stagnant lid. Heat from the interior cannot escape gradually through the spreading of plates. Instead, it builds up beneath the crust until the pressure becomes too great, and the crust collapses and remakes itself entirely. The global resurfacing events that explain why Venus's surface looks so young. Whether Venus ever had plate tectonics is a question that the upcoming missions may help answer. The answer matters not just for Venus, but for every rocky planet. Scientists study because it might tell us how common plate tectonics is, and whether its presence or absence determines whether a world can hold on to something worth calling life. The question of whether Venus was once livable opens quietly, but inevitably, into a larger one. If a planet nearly identical to Earth formed at the same time, from the same materials in the same solar system, if that planet could tip from something close to habitable into something completely hostile, the question follows naturally: how? Many other worlds in the universe have done the same thing. The Milky Way galaxy contains somewhere between 100 and 400 billion stars. A significant fraction of those stars are now known to have planets. Some fraction of those planets are rocky, roughly Earth-sized, orbiting in zones where liquid water could exist. The numbers involved are large enough that even a small fraction of them being Earth-like produces enormous quantities of potentially habitable worlds. But Venus suggests that the mere existence of a potentially habitable world is not the same thing as a world that stays habitable. The conditions required to maintain habitability over billions of years, the right magnetic field, the right carbon cycle, the right distance from the star, the right geology, may be more specific than the conditions required to begin with. Liquid water. The universe may be full of worlds that were almost Earth. The question Venus poses is how many stayed that way long enough for something to begin and then to persist. That question has no answer yet, and the not yet is one of the most alive places in all of science. The Milky Way contains more stars than grains of sand on every beach on Earth combined. This comparison is often offered as a way to convey enormousness, and it does that. But it also does something else if you let it. It brings two scales into contact with each other, the cosmic and the tactile. Stars which are incomprehensibly large and incomprehensibly distant, set beside grains of sand which are small enough to slip between your fingers, light enough to be lifted by a breath. The number of stars in the observable universe is estimated at around 2 trillion galaxies, each containing hundreds of billions of stars. The total is a figure that the human mind cannot genuinely hold. It can say the words, but it cannot feel the quantity the way it feels, the difference between a handful of sand and an empty palm. What the mind can do, though, is feel the ratio. More stars than grains of sand on every beach. Every grain of sand represents a star. Every star represents a possible sun. Around some of those suns, there may be a planet where right now the equivalent of evening is arriving, and something is watching the light change. And feeling, in whatever way feeling works, for whatever that something is, that the sky above it is worth attending to. We don't know if that is true. We only know it is possible. And possibility, when the numbers are this large, begins to feel like something more than speculation. Around many of those stars, planets are turning. The Kepler Space Telescope, launched in 2009 and retired in 2018, observed a small patch of sky containing about 150000 stars and found thousands of planets orbiting them, enough to allow astronomers to estimate that on average each star in the Milky Way hosts at least one planet. Some host more. Some of those planets are rocky. Some of those rocky planets orbit at distances where liquid water could exist on their surfaces. The James Webb Space Telescope, launched in 2021, has begun doing something Kepler could not, analyzing the atmospheres of some of those distant worlds, looking for chemical signatures in the light that passes through them. It has already detected carbon dioxide in the atmosphere of an exoplanet. It has found water vapor. It is very slowly beginning to read the air of other worlds from here. Those distant worlds are not Venus, they are not Earth, they are something else entirely shaped by their own stars and their own geological histories. But they are there, and they are turning. And around some of them, the chemistry of their atmospheres is being read one photon at a time by an instrument humans built and placed in space and pointed at the dark. The sky is full of worlds that someone somewhere is beginning to read. You are made of elements that have traveled an almost incomprehensible distance to find their way into this moment. The carbon in your body, in your DNA, in the walls of every cell, in the sugars that power your thoughts right now, was forged in the cores of stars that burned and died long before the sun existed. The oxygen in your lungs was made in similar stars, slightly larger ones. The iron in your blood was produced in the deaths of massive stars, in supernova explosions, so energetic that they outshine entire galaxies for a few moments before going dark. These elements drifted through space as part of a vast cold cloud of gas and dust. Gravity gathered that cloud, compressed it, and eventually ignited it into the sunday. The leftover material, the disk of gas and rock and ice surrounding the young star, clumped and collided and accreted into planets, including Earth, including Venus, including the small, wet, temperate world where eventually some of those ancient stellar materials found a way to become alive. You are made of dead stars. This is not a metaphor. It is chemistry. The atoms in your body were produced by nuclear fusion in stellar interiors, dispersed by stellar explosions gathered by gravity, and assembled over billions of years into something that can wonder about where it came from. The calcium in your skeleton, in your teeth, your spine, your fingers, as they rest wherever they are resting right now, was assembled inside a star that exploded before the sun was born. Calcium is produced in the later stages of stellar evolution, forged in the cores of stars significantly more massive than the sun, through a sequence of nuclear reactions that builds progressively heavier elements from lighter ones. When those stars exhaust their fuel and collapse, they explode supernovae, scattering their contents across vast regions of space. The calcium scattered by those ancient explosions drifted through the galaxy for hundreds of millions of years before the cloud that would become our solar system began to collapse. It was incorporated into the early Earth as the planet formed. It entered the oceans. It was absorbed by the first marine organisms that built shells. It moved through ecosystems across hundreds of millions of years until eventually some of it ended up in the bones of your distant ancestors, and then in an unbroken chain of inheritance in yours. The stardust in your skeleton is approximately 4.5 billion years old. Every time you have ever held something, a hand, a cup of tea, a pen, you have done it with bones made of the remnants of an ancient stellar explosion. The universe placed something of itself inside you, and you have been carrying it without knowing your whole life. Venus and Earth were born from the same cloud, not metaphorically, not poetically, literally the same vast, slowly rotating disk of gas and dust that surrounded the young sun 4.5 billion years ago contained the material that would become both planets. The same hydrogen and helium, the same carbon and iron and silicon, the same ancient stardust, scattered by the same long-dead stars. All of it gathered in the same neighborhood of the early solar system and began through gravity and collision and time to clump into the worlds we now know. For a while, perhaps a long while in the earliest chaotic period, Venus and Earth were simply two growing piles of rock in adjacent orbits, not yet distinguished by climate or atmosphere or anything that would later matter so much. They grew at similar rates, from similar materials to similar sizes. The same processes shaped them both. And then slowly they became different. The distance from the Sun, just slightly greater for Earth, may have been enough. The initial water content, the rate of volcanic outgassing, some combination of factors still not fully agreed upon, pulled them onto different paths. One path led here to oceans and air, and the quiet sound of breathing. The other led to 465 degrees, and acid clouds and a surface that would unmake any living thing in moments. The same origin, two entirely different outcomes. The gap between them is still being measured. There is an image that emerges when you hold Venus and Earth side by side in the mind. Two spheres, nearly identical in size, traveling in neighboring orbits around the same star. From a distance, from the perspective of another solar system looking in, they might appear almost interchangeable. Two rocky planets in the inner solar system, both with substantial atmospheres, both geologically active, both warmed by the same Sunday. One is blue, covered in liquid water, wrapped in white cloud, its surface a shifting patchwork of ocean and land and ice. It moves through space with the quiet confidence of a world that has found its balance and held it for billions of years. The other is golden. Its clouds are thick and bright and entirely impenetrable from outside. Its surface, invisible beneath them, is a place of volcanic plains and crushing heat and rocks that have lain still since they last broke their edges, unchanged in the eternal amber stillness of that terrible day that never ends and never fully begins. Blue and gold, sister worlds that went in opposite directions for reasons science is still assembling. The difference between a livable world and a lethal one may be smaller than anyone is entirely comfortable with. Scientists do not yet fully understand why Venus and Earth diverged. This is stated plainly in the literature, and it is worth sitting with for a moment rather than moving past it. These are two of the most studied planets in the solar system. Venus has had dozens of spacecraft sent to it. Earth has had centuries of scientific study. And still, the precise sequence of events and conditions that led one to become habitable and the other to become hostile is not completely understood. The broad strokes are reasonably clear. Venus is closer to the Sun, received more heat, possibly triggered a runaway greenhouse effect, lost its water, developed the thick carbon dioxide atmosphere that now bakes its surface. But the details why exactly Venus lost its water when Earth did not, whether Venus ever had plate tectonics, whether its early oceans lasted long enough for anything to begin in them, what the precise trigger was for the runaway warming, these remain areas of active research and genuine disagreement among scientists. This is not a gap in science. This is science. The edge of what is known is exactly where the work is happening. The missions of the 2030s are aimed precisely at this edge, designed to return data that may finally let scientists assemble a complete enough picture to answer what happened. The most important questions take the longest to answer, and they are worth the wait. But the strangeness of the divergence goes further than climate. Venus rotates backwards. Venus has no moon. Venus has no plate tectonics. Venus has almost no magnetic field. Venus has a permanent polar vortex. Venus has a day longer than its year. Venus has clouds of sulfuric acid. Venus may have destroyed its own oceans. Each of these features, taken alone, might be considered a quirk, an outlier, in a solar system full of variations. But taken together, they paint a picture of a planet that has gone in a consistently different direction from Earth, across almost every major parameter that shapes a world's character. It is as though the same starting conditions produced not merely a slightly different outcome, but a fundamentally different kind of world, one where almost every force that on Earth tends toward moderation and balance instead tended toward extremity. The same materials, the same formation process, and yet Venus seems to have taken every opportunity to become as unlike Earth as a similarly sized rocky planet in the same solar system possibly could. That consistency of difference feels almost deliberate, though of course it is not. The universe does not deliberate. It simply allows what physics permits. And apparently physics permits this. Right now on the other side of Earth, from wherever you are, people are watching Venus. Not necessarily with telescopes, though some are certainly in backyard observatories and university rooftops, and dark sky sites where the view is clear enough to make the crescent visible, the phases apparent, the brightness startling, but also simply watching the way anyone watches the sky on a clear evening when something bright and steady catches the eye. In Japan, in Brazil, in Morocco, in New Zealand, wherever the sky is dark enough and Venus is above the horizon, someone is noticing that light. Some of them know what it is. Some think it's a star. Some have seen it all their lives without once wondering what it might be. Some are seeing it clearly for the first time tonight, pointed toward it by a child or a friend, or a moment of looking up that they didn't plan. All of them are receiving the same light. Photons that left the sun 8 minutes ago struck the sulfuric acid clouds of Venus and bounced outward toward Earth, arriving in eyes in every time zone, every climate, every language, every quiet moment of looking up that is happening right now across the surface of this world. The same light reaching everyone at once, noticed by only some of them, mattering differently to each. Every culture that has ever existed has named Venus. The list is long and spans every inhabited region of the planet. The Babylonians called her Ishtar. The Greeks called her Aphrodite. The Romans named her Venus. The Egyptians associated her with their goddess Isis and with the god Osiris, depending on whether she appeared in the morning or evening. The Mayans called her the Great Star, the feathered serpent's light. Ancient Chinese astronomers called her Taibai, the Great White One. In Sanskrit astronomical texts, she is Shukra, associated with brightness and the planet's place in Vedic astrology. In Swahili, she is Zuhura. In Arabic, Zuhra, the radiant. Across 5,000 years, and every continent where people have looked at the night sky, the same bright point of light has collected names the way a river collects tributaries, each one added by a different hand in a different tongue to describe the same thing seen from a different life. The planet has no preference among them. It shines regardless of what it is called, with the same acid clouds and the same reflected light and the same slow backward turning that it has always had. But the names are ours, and in their variety and their consistency of feeling, almost every culture reached for something radiant, something associated with beauty or light or the divine. They are a record of what it is like to be human and to notice something bright in the dark. In the oldest cave paintings found so far at Lascaux in France, at Altamira in Spain, at Chauvet, dated to as far back as 36,000 years ago, the sky does not directly appear, but animals do, and symbols, and handprints, and what appears in some interpretations to be records of astronomical events, dots and groupings, that some researchers believe may represent star clusters or lunar cycles. The debate about prehistoric astronomy is genuinely unsettled. Not all researchers agree that the cave markings represent sky observations. What is not debated is that the people who made those paintings were anatomically modern humans, neurologically identical to us, with the same capacity for wonder and symbol making and the need to record what mattered to them on the walls of the places where they sheltered. They lived under the same sky. They would have seen the same bright light above the horizon that we call Venus, moving through its cycles, disappearing and returning. Whether they had a name for it, whether they tracked it deliberately, whether they felt what later cultures would call wonder, these are things we cannot know. But they looked up. That much is certain. The darkness above them was the same darkness. The light was the same light. 36,000 years is a long time to be the same kind of creature looking at the same sky. Venus is so bright on a clear night that it sometimes casts a shadow, Not the deep, sharp shadow of full moonlight, but a faint, soft shadow visible only in very dark conditions when the eye has fully adjusted and the sky is clear and the ground beneath is pale enough to show the contrast. Under these conditions, if you hold your hand above a white surface with Venus, the brightest thing in the sky, you may, with patience and darkness, and the right angle, see a faint penumbra on the surface below. A shadow, thrown by a world more than 100 million kilometers away. The light that casts that shadow left the sun as ordinary sunlight traveled to Venus, bounced off its acid clouds, with 70% efficiency crossed the space between Venus and Earth, entered the atmosphere, scattered slightly through the air, and arrived at your hand with enough energy remaining to block a detectable amount of the ambient light behind it. Venus throws a shadow. On your palm, on pale ground, on the quiet surfaces of things left out at night in open fields or high deserts. You could go outside on the right night, hold out your hand and receive faintly, barely but genuinely a shadow from another world. The universe reaches you more often than you might think. The atmosphere of Venus is slowly, quietly bleeding into space. Not quickly. Not in any way that would change the planet in a human lifetime, or 1,000 human lifetimes. But the solar wind, the constant stream of charged particles flowing outward from the sun, interacts with the upper atmosphere of Venus and gradually strips particles away. Hydrogen in particular is light enough to be accelerated to escape velocity by this process and lost into space. Over billions of years, this is believed to be one of the primary mechanisms by which Venus lost the water it may once have had, the hydrogen escaping the oxygen left behind to combine with surface rocks. The European Space Agency's Venus Express spacecraft measured this loss rate directly between 2006 and 2014. It found that hydrogen was escaping from Venus at a rate of roughly 1 to 100 kilograms per second, depending on solar activity. The oxygen loss rate was lower, about half that. A world losing itself one particle at a time into the vast, indifferent space around it. There is no drama in this. There is no emergency. The atmosphere is so thick that even at this rate of loss, it would take an astronomically long time to thin significantly. But the loss is real, and measurable, and ongoing. What seems permanent on a long enough timeline is always in the process of becoming something else. Every atmosphere is temporary. Earth's atmosphere will not last forever either. The sun is slowly brightening as it ages, about 10% more luminous every billion years. In roughly a billion years, the sun will be bright enough that the increased heat will accelerate the evaporation of Earth's oceans. The water vapor will enter the atmosphere, where ultraviolet light will break it apart. The hydrogen will escape into space as it did on Venus. The oceans slowly will be gone. This is not a prediction that requires alarm. A billion years is a span of time so vast that the human mind has no genuine purchase on it. Modern humans have existed for perhaps 300,000 years. Civilization has existed for perhaps 10,000. A billion years is 100,000 times the length of all of recorded history stacked end to end. But the arc exists. The process has a direction. The atmosphere holds for now. The oceans stay for now. The conditions that allow this particular evening, this particular breath, this particular quiet, all of it exists within a window, not a permanence. That window is very, very long, and it is open right now. The fact that something will not last forever does not diminish what it is while it lasts. And you are breathing right now, inside that window, on the one world in this solar system that stayed. The air moving in and out of your body contains approximately 21% oxygen, a concentration that exists because of billions of years of photosynthesis, because ancient cyanobacteria flooded an oxygen-free early Earth with a gas. That was, at the time, a kind of pollution. The oxygen in your lungs is the byproduct of life that came before you, released into an atmosphere that was then slowly, over hundreds of millions of years, transformed by it. You are breathing the exhaled work of 3 billion years of life. Venus, in its early period, may have had something similar, beginning water chemistry, the right conditions for something to start. Whether it ever did start, and what happened to it if it did, are questions that remain genuinely open. The missions of the 2030s may find chemical signatures in the deep atmosphere that speak to this, or they may find silence and a different kind of answer. Either way, you are here, on the world that stayed. Breathing air made by life, sustained by a magnetic field, warmed by a sun at exactly the right distance, held in place by exactly the right gravity. The conditions required to produce this moment are extraordinary. The moment itself is ordinary. Both things are true simultaneously, and together they are more than either one alone. The clouds of Venus rotate in the same direction as its retrograde spin. This sounds straightforward until you think about it carefully. Venus spins backwards, east to west, opposite to Earth and most other planets. The clouds, which super-rotate and race around the planet far faster than the surface beneath, also move in this retrograde direction. The entire atmospheric system, from the sluggish surface winds to the racing upper cloud deck, turns the same backward way the planet turns. Why the clouds rotate in the same direction as the planet's unusual retrograde spin is not fully explained. Super-rotation, the clouds moving so much faster than the surface, is itself poorly understood. That both the super-rotation and the retrograde direction are coupled to the planet's unusual spin adds another layer of complexity to a system that is already deeply puzzling. Venus's atmosphere is in many ways the most dynamically complex planetary atmosphere in the solar system. It is driven by forces and interactions that Earth's own atmospheric models only partially capture. Every new measurement taken by arriving spacecraft will be tested against models that have been built over decades, and some of those models will need to be rebuilt. The most beautiful things in science are often not the answers. They are the moments where the data tells you that the model was not quite right, and the whole problem opens up again, wider and more interesting than before. Some of the most important things in science are the questions that do not yet have answers. Not as a consolation for ignorance, but as a genuine recognition that the open question is where the work lives, where the minds are most alive, where the next discovery waits. The questions about Venus, why it spun backwards, why it lost its water, whether it was ever habitable, whether its clouds hold anything biological, what its volcanoes are doing right now, are not failures of knowledge. They are the current edge of it. Every generation of scientists inherits a set of answered questions and a set of open ones. The answered questions form the foundation. The open ones form the horizon. And it is the horizon, not the foundation, that the next mission, the next instrument, the next careful graduate student staying late over a dataset is walking toward. The same is true of any life. The things already understood are real and valuable. But it is the things not yet understood about yourself, about others, about what the next year or decade might hold, that keep the mind oriented forward into something still becoming. Venus, still being understood. A life, still being understood. Both are in the same posture, turned toward what is not yet known, open to what the next observation might bring. Venus will continue its slow backward circuit around the Sun, long after every human name for it has dissolved. Not just the name Venus, but Aphrodite, Ishtar, Zuhar, Taibai, Shukra, and every other name in every other language that has ever been pressed into clay or written on bark or spoken aloud on a clear night by someone pointing upward. All of those names will pass. The civilizations that made them will pass. The languages will drift and change, and eventually become something unrecognizable or fall entirely silent. Venus will still be there, spinning slowly, holding its clouds, throwing reflected sunlight outward in all directions, including toward whatever exists in this part of the solar system in the ages after us. The planet does not need our names to be what it is. It does not need our attention, our missions, our instruments, our wonder. It is not diminished by being unobserved, and it is not enlarged by being named. And yet we name it. We have always named it. We point at it and say that one, that bright one, that light at the edge of the day. Because naming is what we do with the things that move us. It is the smallest possible gesture toward something that matters. The names are not for Venus. They are for us. They are how we tell each other, look at that. It's worth looking at. That quiet persistence, the looking, the naming, the returning to the question may be the most distinctly human thing there is. not the technology, not the science, as extraordinary as both are, but the underlying impulse that produces them, the refusal to stop wondering, the insistence on paying attention, the return night after night and generation after generation to the same bright light and the same unanswered questions. A Babylonian scribe pressing a reed into clay in 1700 before Common Era. Galileo in the autumn of 1610 writing his anagram by candlelight. A Soviet engineer in 1970 watching a signal come back from the surface of another planet for the first time. A team of astronomers in 2020 staring at a dataset and asking, what is that? Could it be? And you right now, in whatever position your body has found, at whatever hour it is, where you are listening to the story of a world close enough to see with the naked eye, and strange enough to take a lifetime of science to begin to understand, all of you are in the same lineage. All of you are doing the same thing. The wondering is the continuity. Tonight the sky above you holds all of this. Every fact that has been named here tonight. The slow rotation, the acid clouds, the lost oceans, the Babylonian tablets, the Soviet probes, the transits observed from tall ships in the South Pacific, the shadow that Venus throws on pale ground. In the dark, the phosphine question, the planned missions, the carbon in your body forged in dead stars, the calcium in your bones scattered by an ancient explosion, all of it is contained in the sky above your head right now. Not as information, as presence, as the actual physical reality of a solar system that is simply there, turning and burning and drifting and cooling and questioning, indifferent to whether anyone is paying attention and somehow always worth paying attention to. The sky does not change because you look at it, but something in you changes, perhaps from the looking. That is not a small thing. That is possibly the whole thing. And somewhere in that sky, Venus is shining. It does not know it is being watched. It does not know it has been named 10,000 times in 10,000 languages. It does not know that human machines have fallen through its clouds and sent back photographs, or that 3 more are being prepared to cross the space between your world and its world in the decade to come. It does not know that someone right now, in a room somewhere on the blue planet next door, is lying still and breathing slowly and holding in the warm dark behind their eyes an image of a golden world turning backward in the ancient light. It simply shines, patient and golden as it has been for longer than memory, longer than language, longer than the first creature on earth that turned its face toward the light and felt something it could not yet name. Venus is shining right now, above you or just below your horizon, or rising in a few hours into a sky you will not be awake to see. It is there. You are here. For this moment, that is enough. Set everything down now. Whatever your hands are holding, wherever your body is resting, let the weight of it settle a little more. You have traveled tonight from the slow, backward-turning surface of Venus to the cores of ancient stars. You have passed through acid clouds and Babylonian clay tablets and the quiet photographs sent back by machines that knew they would not survive. You have touched the calcium in your own bones and understood, perhaps for the first time, or perhaps again, that you are made of something that has been traveling toward this moment for 4.5 billion years. Venus is out there right now, golden patient, turning against the grain of everything around it, holding its heat, keeping its clouds, asking no one for anything, and offering without knowing it everything it has to the curious eyes of a neighboring world. And you are here on the world that stayed, on the blue one. The one with the ocean still full and the air still breathable and the evenings still soft and the strange good fortune of being alive in the window when all of this is still possible. Let your breathing slow a little more. Let the images settle, the volcanic plains, the acid gold, the shadow on your palm, the ancient light. You are part of this, not as a fact to remember, but as something you have always been and will continue to be, long after tonight. The sky holds you, as surely as it holds Venus, quietly, without effort, without end. I hope you sleep well and dream softly. Good night.